Hello everyone, welcome to White Gaming's coding crash course. This was or is a re-recording of the live stream we held on 8/8/2020, just due to the fact we had a few technical issues. Um, so with that, I'll be going through this a little bit quicker and just putting this up as a video for everybody to take a look at later. So uh, all you guys really actually need if you're watching this video is PyCharm 3 or sorry, PyCharm Community Edition and Python 3 installed in order to follow along with this. We didn't actually make it to the Godot standard or the lesson asset pack portions of this tutorial during the live stream, so we're only going to be focusing on 1 and 2. Uh, Links can be found uh, in the description below, or you can go to the forums, you'll find it under our news posts. So, who am I? I am Grotlover2. I am the owner operator of Weight Gaming. I'm also a software engineer IRL, so I spend a lot of time kind of working with this stuff, and I've taught a fair bit of programming throughout my time in college. So, what will we be doing here? Well, we're going to be trying to cover the very basic universal programming concepts. Types and variables, control structures, functions. We might try some high level OOP concepts. We'll go through examples and I'll answer any questions that were brought up in the live stream that I think would be fairly handy for any of you guys to know. But for the most part, if you have any questions, put them in the comments below and we'll try to answer them as we get time to. What we will not cover is Python or any other language specific programming. If it's specific to a certain language, we're probably not going to cover it unless it's something I think needs to be pointed out. We will not be going over software architecture or programming patterns. That's a completely different thing within itself. More complex programming concepts we'll not be touching on. We'll not touch very much on technical details. We will not go into deep magic or heavy wizardry, which is some terms used in programming to describe uh, not well documented features or some tricky stuff you can play with if you have in-depth knowledge about how the hardware works. Uh, which there is some of this stuff in Python, and we're just not going to go into it. And any other programming paradigms for the most part. We're just focusing on what is common. So, what I really want to make sure everybody can take away from this is programs in the end are really just a simple set of instructions. Not even a seasoned programmers can remember every command. It's much more important to know how to search for and reference documentation than it is to memorize everything. And finally, programming is a mindset, not a language. Languages in the end are just tools, and if you can start kind of like thinking in uh, the correct way per se, you will have a much easier time programming and moving from language to language. A few pitfalls and side notes I do want to actually mention before we move forward into the examples is one, flowchart languages. These things are fairly common, especially within game programming itself. It's because they're kind of built for designers on large teams. Uh, these can be a little dangerous to an unseasoned programmer because people will think, oh, it's pretty easy for me to set up a application just by using one of these flowchart languages, but they don't fully understand the restrictions of these languages. Um, with a few exceptions, 90% of these languages, especially like the one in Unreal, which is really well defined out, is meant to be used to set up the general structure of gameplay, but specifics are meant to be implemented on the code level. So if you can sometimes get away with just using flowchart languages, but you have to keep in mind they're actually much more restricted than knowing how to code yourself. And if you want to actually make full use of them, you really need to know how to code still under the hood. The Dunning-Kruger effect, for people that don't know this, it's pretty much that psychological area where you know so little about a subject that you just absolutely do not know how much you actually don't know, which can make you think that you know more about something than you actually do. This is really common within programming because programming has a lot of skill plateaus, especially if you're coming from web programming. Um, it can be very easy to get over one of the hills and end up in what's called a local maxima, and then believe that you kind of figured everything out and you can do whatever you want, and not realize that there is actually a lot more to learn. Um, if you're programming and you ever feel like you know everything, then it means there's a lot of something you don't actually know. So just keep that in mind and never take like, oh, this is really simple for granted. It's You should always be looking to see if you're on that local maxima or not. Uh, Programming can be very opinionated. You can see this especially with like where you're going to place curly braces in C-like programs or tabs versus spaces. The fact of the matter is, standards are very useful when you're working with a team in order to ensure the code remains uniform and easily readable by the majority of the team. But for the most part, just do what works best for you. If you find that one method looks better to you than the other, and you're not working on a team, you just need to do what works best for you. Um, Finally, all example code and the example project won't be on here because we're going to do that at a later date. But all the example code for sure I'm going to be throwing up on GitHub. There should be a link in the description to it if I've got it up by the time this video goes live. Okay, so with that, we can now move on to actually doing some of the examples. So the first example we have here is I am going to be going into what are called entry points and hello world. So for those of you that don't know, hello world is usually the first program any programmer writes, even when they're just starting out. And the main reason for this is because it's a bit of a sanity check program. It's very simple. It checks if input output is working and very, very basic commands are working, as well as that you can actually compile it. So in really like 90% of all the programming courses you'll go through, you'll usually start out with these. So the first thing we're going to do is we're going to create a new function, which we'll get into a bit later. And we do this with the keyword def in Python. Um, then we're just going to call it hello world. And we're going to give this function one command to execute. And what that is it's called print. And we're going to say hello world. So that's pretty simple. To go through this with you, all we're doing, once again, is we're saying this is a function. That's what the keyword def does in Python. Um, then we're saying this is what the function name is going to be. And this right here is the action we want the function to perform, which is printing to the output console this string of letters. Now, the thing is we can't run this right now. We have the code in place, but we can't run it. And the reason for that is because we don't have what's called an entry point. Entry points in software are where a compiled program looks to start its execution. And most C-like programs, it's usually some sort of void main or int main. So you'll see this in things like C++, C Sharp, Java. These are usually the entry points, and that's why main is kind of a pseudo-reserved keyword in those. Um, it gets a little bit more complex than what I told you, depending on the language you're in, but for the most part, that's kind of how it works. In Python, though, it's slightly different. The way you specify entry point is you use this special keyword called underscore name, and you check to see if it is underscore main. And what's going on here is under the hood, this name gets set when it first runs. And if it gets set to main, it means it's looking for the entry point to the script. It's doing its initial startup. So now we'll call hello world. Now, this me so now, as you can see, we've got a little play button here. This is something you get within PyCharm, which is a very good development environment for Python done by JetBrains. And this is just telling us that, hey, this means the script is going to start execution here, and then we're going to call this, which will print hello world. So if we try to run this real quick, as you can see, everything works perfectly fine. So not anything too complicated there. The main point you want to get away from this example is that all programs have to start somewhere, and where they start is called the entry point. And how that entry point defined is varies from language to language, but in most languages, main is always used to identify the entry point to a program. So with that, we're now going to move on to types, which is a very basic concept that uh, we need to go over before we can move forward. So what types are is you are telling the program how it is supposed to, one, store information, and two, interpret that information. As you've probably heard from a ton of people, under the hood, a computer only sees something as a collection of one and zeros, or on and off. So when you give a collection of those binary values data type, you're telling it approximately how many of those it needs and how to interpret that. So for instance, um, here we have an integer data type. It's specified by the keyword int in Python, which is pretty common across most programming languages. What an int does is it says, usually for about 32 bits, which is about 4 bytes in computer memory, that that bucket of memory needs to be interpreted as a whole number. So when it goes and it tries to read that, it's going to take a look at it, and it basically maps the combination of those bits to one type of whole number, whether it be 1, 6, 10, 32, 563, or something like that. A few things to note is types are going to be pretty universal across most languages, with only a very few exceptions when you start getting into more dynamic languages. But for the most part, these stay pretty common across languages. Now, going back to our first value here, first we have the humble int. As I already explained, the humble int is whole numbers only, and it can store both negative and positive values. Uh, Usually, ints take about 4 bytes of space in computer memory, and but there is a few things to note here why you can't necessarily do this in Python. You can specify if an integer can or cannot hold negative values, and you usually do that with a keyword that's called unsigned. What that does is if you see unsigned in front of an integer, uh, that means that it can't hold negative values, and that means it can hold a larger array of positive values. So that can sometimes be handy, especially if you're working with very large whole numbers that you know will never be negative. Uh, in general, though, computer memory is so large anymore that you don't usually need to worry about that. So the humble int is just used by itself 9 times out of 10. regardless. Moving on to our next basic type, uh, we move on to what are called floats or floating point numbers. Some languages have subtypes of floating points called decimals or doubles, which uh, they basically a double is a double precision floating point. Decimal is a specific type of floating point where I believe that most languages have it tend to be a fixed decimal place. And all these are is they're different ways of representing floating point numbers or numbers that are going to have a decimal in them. So not whole numbers or anything like that. Uh, Now, these are handy, especially for percentages, currency, things like that, but you got to be very careful with them. And that is because computers actually can't precisely represent floating point numbers. It's very difficult for them to do. And the standard that actually defines what a floating point number is uses a lot of mathematical black magic under the hood in order to get these to work in what's called a power of two representation, which is how computers work. So to give you an example, 12.5 on some systems is actually 12.4 with 9 repeating. And that's where you can get into some problems because if you wrote a piece of code that was supposed to execute something till 12.5 was hit, exactly 12.5, you would never get there because it would always be 12.4 with 9 repeating. And the way floating points can work can change from hardware to hardware. So that can become problematic when you're doing network programming because if someone's using, for instance, maybe an AMD processor and it goes to someone using an Intel processor, they could handle the floating point storage and calculations completely differently, which results in these rounding issues. Uh, in general, when you're using floating points, especially comparisons of floating points, you always want to make sure you're comparing with a greater than less than just to deal with these rounding errors that occur. It's just something that happens with floating points. It's just a consequence of how computer memory works, and there's no way to get around it. Moving forward, booleans, which are probably one of the most simple primitive types. Booleans are very, very simple. They only hold a true or a false value. They tell you if something is correct or something is incorrect. And they're very useful for flags and different things like that, all where you just want to keep track if something should happen or something shouldn't, or maybe something's turned on or something's not. Moving on, the last primitive type you see in most languages is called a string, which is represented by the keyword str in Python, though is usually spelt out in most languages. Uh, what a string is it's a collection of uh, characters, and these can be in different encodings, which I don't want to get into. But basically, all it is it allows you to just hold different sentences in there and then display them later. There is a bit of a caveat with how strings work. I know I've been using the term primitive type a lot. Primitive types refer to data types that are considered basic within the computer itself. And while strings are considered a primitive type, uh, they're technically what is called a complex type, which we'll get into next under the hood, in which their storage is a little bit more complex than what a primitive type storage would be. Now, one thing to keep in mind is data types. One important thing about keeping track of your types is you can't always perform operations on different data types. So for example here, we have val4, which is a string, trying to be added to val3, which is a bool, and then stored into val1, which, if we remember up here, is an integer. Since every single one of these is different, as you can see, this is being highlighted for me. It's saying, hey, val3 is a bool, or sorry, val4 is a string, and we were expecting another string because when you use the plus on a string, it's called concatenation. But instead it was a Boolean. So if you try to do something here, and if we actually like tried to run this, this would crash because these data types are different. Um, in general, you can only do operations on data types that are the exact same. There are exceptions to that, like for instance, we could add an integer and a float together. The reason why that works is through something called implicit conversion, where the computer is smart enough to realize that, hey, a floating point number is basically an integer, but without this decimal place. So I'm just going to delete this decimal place. Oops. And there, now it's an integer. So that's one thing to keep in mind is in general, you need to be careful about what data types you're playing around with. Okay, so we're going to move on to complex types now. Unlike the primitive types above, which are very simple data structures, uh, complex types are things like arrays, lists, maps, and objects. These are usually much more complex and they require a larger size in memory than most primitive types do. So first, we'll move on to an array. Uh, Arrays are a very simple subtype of complex types called collections. And that is a data type that is meant to hold a boatload of different values in one place in order to access them. Uh, Python itself does not have a concept of arrays. Instead, lists are kind of arrays. But the main thing with an array is arrays take a fixed number of elements and they can't hold any more than that. They can hold less than that, but they can't hold any more than that. They always kind of keep the exact same size. And the main advantage of that is they're very fast and efficient to access. Um, but since their size is fixed, if you give an array of 5 and you need to add like a sixth element in there, you have to recreate the array from scratch in order to hold 6 elements now. So it's not very dynamic, even though it's extremely efficient. A variant of an array is called a list. Lists, unlike arrays, are not a fixed size. You can add elements onto them. You can remove elements from them as you wish. But the main problem is that comes at a cost of speed and efficiency. Uh, Lists don't get the same memory efficiency arrays do because they're not guaranteed to always, depending on implementation, they're not guaranteed to be in the same memory address. They can be spread all around the place. And that's just due to the fact that they increase and decrease their size dynamically. Also, the way they access is different from arrays, so they're slightly slower to access in most cases. Uh, to work with most collections, such as arrays or lists, most languages present them in what is called a zero-based index. The reason for that is because an index is technically the offset in memory from that element. So when you're putting a 0 in there, that means you're looking for the first element with no offset. And then if you put 2, you're looking for the element 2 offsets from where the array starts in memory. So the way this works is pretty simple. Value 1, we're asking for what's at index 0, which is the first element, and that would print 1. If we ask for what's the value at index 2, that's going to get us the third element, and that's going to print 3. So pretty simple. You just got to remember that in most languages, if you're working with arrays or lists, take the element you want and subtract 1 from it. If you want the first element, you want to use the index of 0. If you want the second element, you want to use the index of 1. And that's about it. So moving on, we get into dictionaries, or also known as maps in some languages. These are a really cool collection data structure, and the reason for it is because unlike lists and arrays, which use a numeric index to access data, dictionaries use what is called a key-value pair, where you give it a key and then you tell it what value that key is supposed to tie to. Excuse me. So the as we can see here, what I'm saying is I'm going to have a dictionary with two values in it, and I want test value 1 to have the value of 100, and I want test value 2 to be equal to the value of 300. Now, unlike our lists up here and our array up here where we're using this numeric index, instead we access with a key, which is test value 2. So test value 2 is paired with the value of 300. So if we were to run this, we would have this printing 300. Um, the nice advantage of this is like lists, they are dynamic. They can increase, decrease their size. Um, Two, it's a little bit more self-explanatory what the data is due to being able to use those key value pairs to describe things. So like for instance, instead of needing to know that you need to access the element in index 2 for like, let's say a position, you could instead have a position key and then just access that position. Um, the main disadvantage is once again this flexibility comes at a cost. They are not as fast as arrays for accessing. They require more memory because of how the key values work. Um, and depending on your language, dictionaries or maps can be really difficult to iterate through. Some languages will allow you to do what's called an index access on them, where you can use a numeric index. But other ones, you got to get like all the keys out of them, and then you've got to go and you got to iterate through every single key. So that is one thing to keep in mind, where it can sometimes be a little bit easier working with like a lists and arrays than it's going to be with a dictionary. Now, I know I probably went pretty quick on that, but I do hope that that kind of gave you guys a decent overview of what types are and why they're important. Uh, to give just a quick overview, there's two types. Primitives are very simple data types. They're mainly numbers. And then you've got complex types, which are mainly things like arrays, lists, and objects, which we don't go into here. We do that in lesson 5 when we get to classes. But primitive types are very simple to store in memory. Complex types are more difficult to store in memory. So it's kind of just think of it that way. These guys are simple. These guys are complex. So moving on, we are going to now go into our control structures. And once we go through our control structures, we're going to go into our first kind of major example where we're going to do what's called a bubble sort algorithm. So in general, there are two categories of control structures. You have if statements, which allow you to make decisions in a block of code, and you have loops, which allow you to repeat a set of instruction till either a set condition is met or like a number of iterations have been performed. So the first one is going to be an if statement. If statements are very, very simple. You give it a condition. If that condition is true, it will perform that command. If it's false, it will not perform that command. So moving through here, we have our first if statement. We're asking if false is true. That's all this statement is asking. And if false is true, then we're going to print this will never be called. Well, since false is obviously not true, something that's false cannot be true, um, this line of code here will never ever be called. But if we look to the one below it, where we're asking, is true true, which obviously it is, true is always going to be true, we say, then print this code here. This will always be called. And as you can see, since true is obviously true, this would actually be executed. And if you're wondering about what these highlights are, these are just telling me that, hey, this code is unreachable because this condition is always going to be false. So that's a good way to figure it out too. Uh, Now, you don't have to just be using Boolean values. You can use any type of value for comparison. So for instance, here I'm asking, is 3 greater than 0? And the answer to that is yes, 3 is, of course, greater than 0. Since the answer that is true, then we would end up printing this statement right here without any issue. Now, if statements are very useful, but if you were only able to compare one thing at a time, if statements would get really, really messy, and you couldn't really get very, they wouldn't be as powerful of a control structure as they actually are. So you can combine conditions together in an if statement using two different keywords, an or and an and. What an or does is an or says one of these conditions has to be true. I don't care which condition it has to be, but one of these has to be true. An and condition says both of these conditions must be true. If either one of these conditions is false, I'm not going to do anything. So uh, let's start off with an and first. So we're first asking, is true true, which obviously it is. So since it's true, uh, and we see there's an and here, the if statement knows it's not done yet. It's going to now check this second statement, and it's going to ask, well, is 1 equal to 2, which 1 is not equal to 2. Since this is false, but true is true, the and says both of these have to be true. So in the end, the entire statement's false. So this never, ever gets called. And we can do that as many times as we want. If we want to put a third one in here, we can ask if 1 is greater than -3. So you can do this with as many as you want. It's just all these have to be true in order for the statement to move forward. Uh, Moving down here, we have one where we're saying is 1 equal to 1, which is true. And then we've got that and statement there again. So the if statement now knows that, hey, I can't just execute this code. I need to go check to see if 1 is unequal to 2 as well, which is true. And since both of these are true, the if statement is now like, okay, we can actually do this now. So it will now print, this will be called when it runs. Now moving on, we get to the or statement. And like with the and, it allows you to concatenate things together, but as explained above, only one of these statements that are ORed together needs to be true. So for instance, is true true? Yes, true is true. So it actually stops evaluating right there since that's true, and it will immediately print this, no problem. It doesn't matter that 1 is in fact not equal to 2. Since only one of these has to be true, then it's going to call it anyway. Now, if I change this to false, you see that this goes yellow because we can't use this anymore. It doesn't matter. But if I do or, I say 1 is equal to 1, there we go. Everything's happy, everything's pretty. Because this would be false, this would be false, but 1 is equal to 1, so I am happy to execute this without doing anything else. And you can see this here. If both the conditions or all the conditions within an OR statement are false, that code will never get executed. Now, there is another logic operator you can use to modify how the logic works, and that is called a not operator. In most languages, the exclamation mark is used to simplify a not. In Python, the actual word not is used. And all it does is it inverts the logic. It makes what is false true, and it makes what's true false. So if we take a look here, is 1 equal to 2? The answer to that is no, it's not equal to 1 is not equal to 2. But we're checking if it's not if 1 is not equal to 2. So since 1 is not equal to 2, then this is actually true, and we would end up printing this would now be called. Now, while if statements are really powerful on their own, sometimes you want to just make sure there's some logic that gets called when uh, it doesn't match, but you don't want it to be called all the time. So, for instance, maybe you want to print that 1 is not equal to 2. Well, if we were just using an if statement and 1 was equal to 2 for some odd reason, um, we would print that 1 was equal to 2, and then we'd print 1 is not equal to 2. So that could be confusing, as you can see. In order to assist with that, if statements can be paired what is called an else statement. Now, an else statement provides a default piece of code that is to be executed if the if statement itself is not true. So if we step through this example right here, the code first asks, is 1 equal to 2? It's not. Since 1 is not equal to 2, it jumps to this else statement and it runs this print. Now, if we were to change this to if 1 is equal to 1, what would happen is it would say, yes, this is true. It'd run this print statement instead, and it would skip this entire else block. So that's kind of the big thing with else statements is they allow you to define a piece of logic that should run or a piece of code that should run if the value itself is not true. Now, you can chain multiple of these together in what is called an else if statement. In most languages, else if is legitimately used. In Python, the keyword elif is used for else if. Uh, what an else if statement does is it says, first, is this true? No. Then it'll check the next statement and then the next statement. And it will keep going till it finds the first statement itself that is true. And when it does that, it's going to stop executing. And you can still have an else in there for if everything in here turns out to be false. That is one of the key things to keep in mind with this, though. Else if statements stop their execution on the first true statement they hit. So it doesn't matter if you've got 600 of these. If you hit if the first 6, if like in the first 3 you hit a true statement, it'll stop executing. It'll skip the remaining. Now, one thing I do want to note here, and it is something I do dislike about Python, unfortunately, is many languages have a variant of an else if statement called a switch case statement. Switch case statements work mainly on simple types. It does depend fairly heavily on your language, though. C and C++, for example, really only their switch case statements only work on primitive types, where C#, for example, can do a lot more complex comparisons on their case statements. The thing is, switch case statements are technically also more efficient than an else if statement. The compiler does some little black magic under the hood to deal with that. And in reality, most compilers will kind of convert a big else if statement into a switch case if they can. The main disadvantage with switch cases is you don't get things like ands and ors in there. It's literally trying to match a value to there. So for instance, this is a switch case statement in most C-like languages. This would work in C#, this would work in C++. I'm pretty sure this would work in Java. And all I'm saying is, okay, the value is 15, and then what I'm saying is here, is the value 1? No. Is the value 15? Yes. So it'll print the break, it'll print there, and then when it hits this break, the break tells it to stop executing, and it runs out of the switch state. So they can be really, really nice, especially if, for example, you have what's called a finite state machine, which is common in game AI, because you can put the current state in that switch state, and then it just adjusts what is going to be running at that point. So moving on, we move on to the second biggest part of programming control structures, and that is going to be loops. In general, there are two general types of loops within most languages. You have the while loop with its variant called do while, which I'm not going to go into, and a for loop. Now, a while loop is pretty simple. What a while loop does is you give it a condition, like with an if statement, and all it does is it keeps on looping over and over again till the condition is no longer true. So what we're doing here is we're saying, okay, we're going to have this variable with a type of integer, like we expressed back up in lesson 2 with types, and we're going to say, while the num is not equal to 10, keep on looping this. And then we're going to go grab another random number. So this is going to keep on looping until we get a roll where we get that number set to 10, and then it's going to stop doing it. It's just going to break right on out. While loops are very handy for what is called an unbounded iteration, when you need to loop over something over and over again and you don't necessarily know how many times you need to, you just kind of know the conditions where it needs to stop looping. For loops, which are a lot more common because in general, you usually don't have unbounded iterations, you have bounded iterations. But a for loop, they iterate over a set list of elements or they iterate over a set number of items. There are two variants of a for loop in most languages. It's called a for and a for each. In Python, they're both kind of the same exact thing. They're just a for. A for each loop will iterate over elements. A for loop will iterate over a set number of items. Most for loops follow the format of a counter, a condition, and an increment. Uh, and once again, for each loops, we'll go over collections. So to give you an example here, what we're doing here is we're creating, what range does is it creates a list of numeric elements between 0 and 10 for us. And what we are saying is for each number in this list that gets produced, assign that into the variable count, and then we're going to print that. And that's pretty much all for loops do. They're pretty simple and they're really, really useful for doing that sort of stuff. So with that, what we're going to do now is we're going to create a new Python file. And we are going to do a bubble sort, which is a very, very simple sorting mechanism that will allow us to play with these control structures and give everybody a bit of a better idea of how they actually work. Because I don't know about you, but when we get to use these a bit more in practice, they make more sense to me than necessarily being lectured at. So as you can see, the first thing I do here is if name equals main. If you remember back to lesson 1, I'm defining our entry point. I'm telling Python this is where we need to start execution when the program runs. So the next thing I'm going to do is I've actually got a small random list over here that I just hard coded. So I'm going to copy that over, and there, we're going to have this random list of values, and we're going to now write some code to actually go through and sort it. To ensure that the random list is what we expect, we're going to print it before we do anything. That way we can actually just go through and figure out everything that's going on. So the first thing we need is we need a way to keep track if the list is sorted or not. So the way I'm going to do that is I'm going to create a variable called isListSorted. I'm going to tell it that it's going to be a Boolean value. I'm going to set it to false because the list is not going to be sorted when it first runs anyway. Now, we don't know how many iterations a bubble sort is going to work because what a bubble sort does is it'll take a look at the two values kind of next to each other and it'll flip them. And it'll just keep going across that list if they're greater than each other till the list is fully sorted. So since we don't necessarily know how many iterations that's going to take, we only know the condition where we want to stop doing that. we need to use a while loop. So we say while not is list sorted. So as you can see, I'm using not. This comes back from our if operators, if you remember correctly. It inverts the logic. It inverts the conditional logic. So what is true is false and what's false is true. And the while loop is just going to keep moving over and over again. So at this point, what I'm telling the code is while the list is not sorted, keep on looping over it. So what we're going to do now, and this is what is called an optimistic approach. We are going to assume that the list is sorted as soon as we actually get into this loop. So we're going to set that the list is sorted to true. Now, what we need to do though is we need to do two different things here. We need to, one, look to see if the list is in fact sorted, and if it is not, we have to start moving those values with each other if they turn out to be larger than the others. So for instance, 45 and 2 would need to get swapped, 2 and 1 would need to get swapped, etc., etc. Now, since we know the number of elements we have to go through, this is a prime candidate for a for loops. So we're going to say, let's use a better name than x. Let's say index. In range, oops, sorry, I wanted to do this. And we're going to start from the first index and not, or we're going to start from the second index and not the first index. So due to that, we're going to use 1, and then we're going to say to the end of the array. And the way you do that in Python is using what is called the length method or function. And then we pass in our list. So we do random list. So what this is going to do is this is going to get us a range of numbers between 1 and then how large this list is. So 1, 2, 3, 4, 5, 6, 6. So with that, the first thing we need to do is we need to check if, oops, if I spell this right, if the previous element, which is going to be index minus 1, this is why we started out at 1, by the way, and not at 0, because we're applying this minus 1 because we're going to check the element behind the current index, is greater than the value in the current index. If this is true, if, for instance, 45 is greater than 2, what we are going to do is we're going to make a new variable called smaller, which will make that an int, because all these above there are integers. And we're going to go and random list and index, because that is going to be the smaller value. And we're going to make a new one called larger, make that an int, grab random list, and we're going to do index, once again, minus 1. Now, the reason why we do this is because now we're going to flip them. So what we're going to do now is we're going to say random list index is going to become the larger value, and random list index minus 1 is going to become the smaller value. See, pretty simple. And now there's one last thing we need to remember to do here, because if we don't do this, it's going to just loop through once, and then we're not going to really get anything. Like 45 is probably going to end up at the end, but 2 and 1 are still going to be out of position along with everything else. And what we need to do that is we need to say is list sorted and set that to false. Ta-da! So what we're saying, to go through real quick, just go over the logic. What we're saying is, while the list is not sorted, I want you to keep executing this code over and over again. We are going to assume that the list is sorted unless told otherwise. I want to go through every element in my list, and if I find an element where the element before the current element I'm looking at is larger than the current element I'm looking at, then I want to flip them using this, And then I want to tell the system that, no, we are in fact not sorted yet. We need to loop through this again. Now, to ensure everything works correctly, we're going to print and we're going to say random list. Now, if the demo gods smile upon me and I run this, we should see, and voila, there we go. We start with this random list and it gets sorted correctly. We've got 1, 2, 2, 5, 12, 45. And that's how you implement a bubble sort. And hopefully this helps you get a better idea of some of the basic control structures. So with that, we now get to move on to functions. Now, functions are really nice. And the reason for that is because functions allow you to group repeated commands together so they can be more easily called. So for instance, square rooting something, or maybe you just got something that prints to a log file pretty consistently, stuff like that. So moving through this, the main first thing is functions usually always come in three parts. And this is a little bit different in Python, but I do want to show you how it is in C-like languages since they do tend to be the more prevalent languages. You usually have your data type, oops, followed by your function name, open parenthesis, your arguments, followed by a close parenthesis. So, for example, in let's say C#, a function would look like this. If it wasn't to return anything, we'd say it was a void. My function would be the name, and int x would be our argument. So that's generally how functions work. Now, or look, in Python, they're slightly different because they require the use of this keyword called def. And all def means is define. So you're just saying define this function. You can tell it an explicit return type as well, but for the most part, like if you omit it, it's assumed that it doesn't return anything. So to go through here, what this is we're telling Python to define this function with the name print message, and it takes no arguments and it returns nothing. And all it does is it prints this message, and that's it. Now, this one right here, we have a little bit more functionality with. What we're once again saying is with the def keyword, we're telling Python to define a function called say hello. But this time we've got this in here. Now, what is this? This is our argument list from what you saw in the previous example when I was going through the C-like syntax. We're saying that this is going to be a variable by the name of name, and it's going to have a data type of string. And what this function does is it prints hello with a space, as you can see right there, and then we append the name to it. So it would be hello Anna, or hello John, or whatever. So you would just throw that in there and it just automatically append it. Now, if we move on, we get into something a little bit more complex. And this is going to be a function that not only takes in a value, but it returns something back out of it. In a C-like syntax, this is how it would work. So, a C-like would look like this. Float square float value. Now in Python, this is how that's going to look like. What we do is we say, okay, define me a function, and I'm going to call it square. It's going to take in one argument called a value, that is going to be a floating point number. And this little arrow here is how we tell Python what it's going to return. Float. So then we return the value multiplied by itself. So it creates the square of the value. Now, we can also allow functions to take multiple arguments. So for instance, we can put in multiple different integer values. You can do it with a lot of different things as well. They could be floats, they could be booleans, they could be strings, they could be whatever you want. So what we're saying here is we're saying define me a function that says equals. This first value is going to be an integer. This first value is named value 2. It's going to be an integer, and we're going to return a bool. And this is actually a very common function you kind of see in C Sharp because C Sharp does a lot of things with equals under the hood. And what we're basically saying is tell me if value 1 is equal to value 2 and return true or false. So see, simple. If we were to do this in a C-like syntax again, just so everybody knows, this is how this would work. It would look like bool equals, oops. So as you can see, it's like the structure is not too different. It's just a little bit of a different syntax to the more prevalent C-like languages. And that's kind of the big thing I want you guys to get out of this is not necessarily how to set up the functions, but like what functions are, and that is a collection of commands that need to be executed over and over again, and kind of their individual pieces. Your function name, your arguments, and the return type. That is universal across almost every single language. It's just a little bit different in setting them up. Now, one thing, this is where we're going to get into some stuff that is a little bit more icky, and can kind of get a little bit more confusing. Some functions are able to change what is passed into them in the arguments. Uh, this doesn't usually happen, but whether or not an argument can be changed depends on whether they're what is called mutable or immutable in Python. In most other languages, especially C-like languages, these are known as passed by value or passed by reference. The main difference is something that is passed by value, a new copy of that value is created when it is passed. So if you pass in a numeric value of 1, it creates a brand new numeric value of 1 somewhere in computer memory. So if you change that, it doesn't change the original at all. When you pass by reference, though, or when something's mutable in Python, what you are doing is you are not making a new copy. You're instead saying, hey, if you need to access this value, this is where you find it. You basically give it an address to go look at. And that means if you change it, you change the original value. So as you can see here, I've got this kind of defined out if you want to read it on the GitHub repo once I get it up. But arguments are passed by reference, also known as mutable in Python. They do not make a copy of themselves, but instead refer to the original. And this means if you change it, these types in the argument will change the value of the original. In general, most modern languages will usually use base primitive types by value. I'll always pass them by value. And more complex types like collections and objects will be by reference. This isn't true for every language, though. Like, for instance, C and C++ force you to explicitly specify when something is by reference. Otherwise, it will always do it by value. There are some exceptions to this, but I'm not going to go into. C# gives you an explicit way to pass something that's usually by value by reference. Java, if I remember correctly, does not allow you to do it whatsoever. They've got fixed rules in place and they expect you to play with it with those rules. So moving down here, we have this function called fuck with the list, and we're passing in a list of values, which is the mutable type in Python. So that means under the hood, it's getting the memory reference to this. So, and then what we're doing is we're setting the first index or the first element in that list to -1, and then we're setting the value at the very end of it to -1000. So now to just show you, we'll run all these real quick. And we're going to ignore all these. These are our other ones up here. We're more interested in these. So as you can see, this is the list before we threw it into that method. The first element is 55, the last element is 0. And as you can see, we didn't return anything out of here. We're not actually assigning anything back to test list. But since it is by reference, when we set the first element and the last element like that, you can see that it is now -1 and -1000. So that is by far one of the hardest things people will have actually getting their heads around. It has caused so many problems. So if there's anything you want to really try to remember from this lesson, is this pass by value by pass by reference. Um, I don't expect anybody to be watching this, since it is a crash course, to necessarily remember this on their first viewing, especially if they're brand new to programming, but it is something you need to be aware of, because it's very common for like an object to change out from underneath you and you wonder why that happened, and it's once again usually because it was passed by reference and you modified one of the properties on that object through that reference. Okay, so with that, what we're going to do now is we're going to make a new bubble sort. But this time we're going to use what we learned from functions. So we're going to do functions bubble sort. So the first thing I'm going to do is I'm going to copy and paste some stuff just over here, because I don't necessarily want to type it again. So what we're doing here, once again, this is our entry point. We're saying the script starts here. This is our random list, and we're going to call a function called bubble sort. So let's define out bubble sort. So bubble sort. Now, what would we need for bubble sort? Well, we're sorting a collection. So we obviously need to bring a collection into it. So we're going to make a collection, which is a list. Now, do we need to return anything out of this? The answer to that is no, we actually don't. And the reason why is because we're going to leverage the fact that lists are passed by reference to modify the collection, as opposed to caring about returning it back and reassigning it. There is good reason to do this. It comes down to performance, but I'm not necessarily going to go into that. So like in our last one, what we're going to do is we're going to create a new Boolean value to keep track if the list is sorted. And we're going to make it false to ensure that we run this once. And I see I screwed that up there, so there. Now we're going to make a while. So while the list is not sorted, we want to go through here. We're going to assume that the list is sorted, because we're going to be optimistic here. And then for index in, and once again, if you remember last time, this is from the first element, or from the second element, not the first element. So from 1 to the length of the past collection. Now, if collection index -1 is greater than collection index or smaller, which will make an int, equals collection index, because that is going to be the smaller value, and our larger value, which will also still make an int, just to keep everything nice and same, will be the value before it, or the element before it. We now flip them. So the one we're currently looking at becomes the larger, and the one before it becomes the smaller. And then we set that flag is list sorted equal to false to tell the system that, hey, you need to go over this again and make sure everything looks like it's set up correctly. And we'll put another one in here. So now if I set this up correctly and we run this, everything should hopefully run correctly. Let's take a look. And there we go. As you can see, our bubble sort ran correctly. All the values get nice and sorted. And we have this nifty little function that we can call anywhere we want. We don't need to rewrite this code 1,000 times because we can just call it anytime we want to use bubble sort. So if we had maybe a random list too, we could do that without having to rewrite everything. So this is why functions are really powerful, because they allow you to reuse this code fairly easily. Okay, so with that, we're going to move on to the final lesson. I know this has been a little bit long, and that's going to be classes. Classes are by far one of the hardest concepts to get within programming. But they're extremely handy. They're for a programming paradigm known as object-oriented programming, and it is where you abstract ideas into functional objects. So, for instance, a circle, you would abstract a circle into what is a collection of its radius and maybe a few other mathematical formulas that represent a circle. So classes, which are also known as custom size, they're good for organizing more complex data into reusable packages. Classes can contain two general categories of data: properties, which store data. These are things like our usual primitive types, and methods, which define actions a class can perform. These are basically functions for the most part. Classes can be used to create a version of itself called objects when a program runs, and each object is unique when they're created. It should be noted that most languages allow you to specify access levels of properties and methods. This allows you to prevent people from toying with internal logic of a class without necessarily knowing about it. A private is used to say a property or method should only be available to the class itself. Protected says it should be available to things that inherit that class as well as the class itself, which gets into the inheritance hierarchy stuff. And then finally, public says that the property or method should be available to everyone and everywhere. So unfortunately, though, Python instead relies on naming conventions for this to communicate intent. So, for instance, an underscore in front of a property or method usually is used to communicate it as private or protected, and should not really be messed with. So, to go through some of this real quick, we'll go over a basic class. So, this right here is a very basic class. First, we start with a class keyword. This is very common in a lot of languages that you usually define a class starting with a class. And then we say the name, basic class. This class right here contains two properties. They're private because of that underscore. And we're saying var1 is equal to an integer and var2 is equal to a float. Now, all classes usually contain what is called a constructor. In Python, constructors are defined as underscore underscore int underscore underscore, though in a lot of C-like languages, they're more like public basic class, which would be a constructor, which you can see what this would look like in a C-like language here. Now, this is kind of one of the weird things about Python you need to keep in mind. You don't get, usually this is hidden in most modern languages. It gets passed around for free. But what self is a reference to the current created object. So when you pass in self, you're telling it this is what the object I'm currently working with is. Then we have var1 and var2. These are our arguments for our constructor. So what we do here is we say when we make this basic class, we want to save var1 and var2 into our var1 and var2 properties. Now, there's a different constructor type method called a destructor. And what destructors do is these are methods that run instead of on creation, they run when the object is destroyed. So for instance, right here, all we're doing here is we're creating a destructor, which in Python you do with the underscore underscore del underscore underscore method, where in most modern languages, if you do in most C-like languages, most destructors are prefixed with a tilde, which is that little squiggly line above your right next to your 1 on your keyboard, and then usually the class name. And all this would do is when this gets disposed of, it will print a string that sums our two private values together and then says has been deleted. And then right here is one of our methods. As you can see, this is public because we don't have an underscore in front of it. And we're passing this object in. So it doesn't take any arguments. It just takes the object. And then we're returning a floating point value from it. And all we do is we basically take var1 and var2, whatever it's been set to when we created this object, and we add them together and we return the value. So if we take a look here, we create a new instance of our basic class, and we give it the initial values of 10 and 12.3. And then we print what that sum is. So if I was to go run this real quick, as you can see, the sum gets us back what we expect, 22.3. And then when we explicitly call delete, which is us getting rid of the object, it calls our destructor up there, telling us that it has been deleted. Now, one thing to keep in mind is you want to be very careful about explicitly calling delete on objects. The reason for this is most modern languages use what is called a garbage collection system under the hood that kind of knows when an object is no longer being used and will clean it up for you automatically. If you explicitly call this and then you try to do something on it again, like let's say sum, we try to sum again and we run this, what's going to happen is we're going to get a crash. See right there, BC is not defined. And the reason for that is because we've deleted BC. In general, you don't want to explicitly delete objects unless you have a very good reason for it. Unless you're working in C++ where you have to do that. Otherwise, kind of just let the garbage collector handle it for you. So like if I go and I get rid of this, and I run this again, as you can see, our destructor is still being called. And the reason for that is because as soon as we exit the main method, the garbage collector knows that this object is no longer being used and it deallocates it back to the heap. So fairly simple. Now, with that kind of out of the way, we're on the final leg of this entire journey. So we're going to do one more example. And what that is we're going to make a new example using classes in order to kind of drive some of these points home. So let's say we are going to make a new game. And And in this game, we're going to fatten up some people, the usual stuff. So we do this here. We first define our entry point, and I'm going to use a keyword in Python called pass, just as a placeholder. What pass is it's called a no op or a no operations operator. And all it does is it basically consumes a CPU cycle and does nothing. You can find these actually in most languages, though they are usually literally no op. So the first thing we need to do is we need to figure out, well, how are we going to, if we're going to make someone larger for exit, if we're going to make someone fat, we need to be able to feed them, right? So let's start with that first. That seems like a good place to start. So what's fattening? Baked goods. So we'll do baked good class, which will allow us to define a boatload of baked goods that we can use to feed people to make them fat. So we'll do name. We'll say they have to have a name, and we'll have a value here which represents how fattening that baked good is. And since we want to make sure these are always set, we'll make a custom constructor where the person needs to define what the name is going to be. Oops, my bad, I meant that to be a string. And how fattening it is going to be. So self.name is going to equal name, and then self.fattening is going to equal fattening. So there we go. We get this set up, and our baked good object is all good and ready to go. So now we need to be these things are cool and all, and like I'm going to copy over a few of the baked goods already from my little example file. So I'm going to highlight pass, and there we go. We've now got cookies, we've got cupcakes, we've got pie, and we got the calorie bomb. Now, we've got all these baked goods, but we can't necessarily, like, they're useless if we don't have someone to feed them to, right? So what we could do is we could go and we can make a person class right off the bat. And we can make them capable of eating baked goods. But what if maybe we want to do something else? Maybe people are not the only people that can consume these baked goods. Maybe a dog could or something like that. So the better thing to actually do is make what is called a consumer class. And what we'll do here is we'll create a value called weight, which will keep track of the current weight of the consumer. So we'll create this here. This is called the default constructor because we don't have any values in it, and we're going to set that the weight should always start out at 160 pounds. Now we need a few other things here. So we need a method to be able to eat these foods or these baked goods. So we'll say food baked good, and then what's going to happen is we're going to take the weight is going to equal self.weight plus the food, how fattening the food is. And then we're going to make this, which will tell us the current weight of the consumer. So with this consumer class, what this allows us to do is we did what's called abstraction. We abstracted out all the stuff that would be necessary for entity that can eat into one little package that we can reuse. So if maybe we don't want just people to be consumers, maybe we want enemies or monsters or anybody else to also be able to consume these baked goods, we simply we extend this and we're good to go. So moving on from that, what we're going to do now is we're going to implement the actual person class. So if I do class, and I'm actually think I just like two spaces right there. If I remember, that's the way Python tends to like it. Now, what I'm going to do now is I'm going to make a new person class, and this person class is going to extend the consumer. And the way you do that in Python is with these parentheses and then consumer. So now we've got this person class, and it's an extension of the consumer class. So what does a person need? Well, a person needs a name. And let's also just put a gender in here because we need some more information. So gender for the person. So what we're going to do is we're going to first make a brand new, and that should be init, not int. I made the same mistake up there. But we are going to make a constructor. So the constructor is going to take the name, and it is going to take the gender. And you don't necessarily need to keep track of gender. I just need some more data for demonstration purposes. So we're going to say, okay, give me your name, self. We're going to take gender. We're going to equal your gender. Okay, cool. So, and then also to ensure that the weight gets set correctly, what we're going to do is we're going to go super and then init. And the reason why you do this is super means call this class, the one you're inheriting from. So we're calling this one right up here. Simple. Now we're going to give a person the ability to tell us their name. So we'll create a new method called sayName, and we're going to print this line, which I am just going to pull over here. So what they'll say is, hi, I am their name, and I am and whatever their gender is. And then we're going to make a new method, and we're going to call this talk. And this is just going to allow our person class to talk. And I'm just going to copy these over because I don't necessarily want to type them all out again. But we're going to use a bunch of else if statements in order to change what they say based on how heavy they are. So if they're under 200 pounds, they're going to say I'm quite thin. If they're under 300 pounds, they're going to say they're getting chubby. If they're under 400 pounds, they're going to say they're getting fat. If they're under 500 pounds, they're going to say they can barely stand. And if they're anything over 500 pounds, they can't move anymore. Fairly simple. Now, we're going to create two new things here. And actually, I forgot that this happened on the live stream, so I'm actually going to do this real quick. This shows how you can kind of abuse these types of things. Instead of using a traditional gender in that field, instead we made a type. So this person is Moline and they are FD, and this person is Bob and they are FD. Which was actually really clever and is something I want to keep in here because this is actually quite common when classes you make, especially in libraries, will be used in manners like this, where they don't really care about the gender, so it was just, hey, let's put FD in there because it only affects what this is going to be in there. So I'm going to copy now over some more code in there, and we're going to have, and this is going to be the rest of our method here, or our intro point here. So we've got this buffet, which is going to hold some cookies and cupcakes. We're going to take Maline to the buffet. We're going to ask them to talk, and then we're going to basically feed them. And we're going to use a function in order to show why the consumer is so handy as opposed to using a person class. And then we're going to get them sucked. Then we're going to do the same thing with Bob. We have Bob's Burgers, which is going to have all this stuff in there. So with that, we're now going to finish the last part of this. And we're going to create a new function called feed the feedee. So we're going to go with the feedee. And see, we're giving it a consumer type as opposed to a person type. And then we're going to get the baked goods, and we're going to give that as a list. That's the way we can feed the feedee multiple items at once. And then it's going to return the consumer back. So what we're going to do is for each piece of food in the baked goods that we sent in, and I see I made a typo, so let's do that. And then we're going to have the feedee eat that food, and then we will return the feedee. And see, this is nice. This function doesn't care about their name or any other information. It just cares if it's able to feed that thing. So this allows us to set it up just like this, and it'll work perfectly fine. So if I run this, and once again, if the demo gods are good to me, there we go. So as we can see, we get Milling, they are a feedee. They say I am quite thin. So we feed them buffet, and then they say they're getting fat. So then we have Bob, who says he's a feedie. I am quite thin. And then, well, it turns out Bob went a little bit crazy, and he can't move anymore. So that's kind of how like objects can be used. They're really, really handy, and like because they allow you to centralize common properties and functions and kind of organize them in a way that makes sense. And like here's another thing, like so I'm not into vor and myself, but let's say you were into vor. Um, if we go here, we add baked good on there. Uh, the funny part is technically, even though there is some stuff I need to do here, but technically the person class is now baked good. And that means you could actually have a person eat another person, and there you go. You just got vor in your game. So objects are just really, really, really powerful, and due to that, they're good to kind of wrap your head around, especially with the games we tend to make, where this stuff can be really difficult to kind of keep track of, especially when you're working with multiple characters. So with that, um, I would like to thank all of you for watching for the most part. I do understand that this is going to be a lot of info for most of you watching this to probably take in. It is a crash course. It's not necessarily meant to be really, really in depth. It was meant to just kind of give a high level overviews of some standard programming methods. Um, If you do have any questions, ask them down in the comments below or on our website, waitgaming.com, and we will get to them pretty much as quickly as we can. You'll get a more immediate response from the programming section on waitgaming.com than you'll get in the comments of this video. But for the most part, I do hope this was helpful. We are hoping and planning to do some more live streams and some more in-depth videos instead of just these crash courses. where we go into some of these in a more in-depth manner where we can explain the intricacies and kind of work through with people. But if you're interested in our live streams, our dev streams, or anything like that, keep an eye on our website or our Twitter. We'll announce them there. If you're in the Discord, feel free to hit me up with any questions you might have. With that, I'm sorry this took so long. The game jam took more time to organize than I kind of expected, but I hope this proves useful, and I wish you all a good day.